Does a defect in your cell phone screen or liquid crystal display television drive you crazy? A recent study on the space station is learning more and more about liquid crystals, and it could change the future of screens and other things that use liquid crystals. NASA commentator Lori Meggs has more from her visit to the Telescience Support Center at Glenn Research Center.
I'm here with Nancy Hall. We're in the Telescience Support Center at Glenn Research Center where OASIS operations are underway. You're the project manager for that.
Yes.
That's going on behind us right now and on
Yep.
the space station. But we're not far away on a desert island like an OASIS. What
No.
are we talking about?
We're talking about liquid crystal experiment. OASIS stands for Observation and Analysis of Smectic Islands in Space. And a smectic island is just a different configuration of the liquid crystals. Most people are familiar with solids, liquids, and gas. Well, a liquid crystal is in between a liquid and a gas. It behaves like a liquid, but its internal structure is like a solid. So smectic islands is just one part of it.
So is this something like we see LCD, that's our TVs,
Yes.
on our phones?
Exactly. When you
Okay.
think of liquid crystals, an LCD display is a liquid crystal display. So we're trying to better understand liquid crystals, how they behave, what happens when you manipulate them. In our experiments, what we're going to be doing is the liquid crystals will actually be housed inside this bubble chamber, which we call the inserts. And we're actually going to be looking at 4 different types of liquid crystals. And what we're going to be doing is manipulating it. If you look at this side here, there's a camera, there's a window, and we'll have a camera that'll actually be able to see the whole bubble. The bubble's about 15 centimeters in diameter. And then on top here, we have another camera that's going to look down, and it's going to look at a smaller portion. So this will have a 20 times microscope that'll focus in on a key area so we can actually look at the individual layers of a liquid crystal.
Is this the first of its kind study where we're looking at liquid crystal?
Yes, this is the first liquid crystal experiment, but it won't be the last. We have a series of liquid crystal experiments that's going to follow it, so we're looking forward to that.
And so the folks behind us here are busy at work. They're gathering the data coming from this experiment.
Yes, they're gathering the data. In fact, the operations is happening right now on the space station, and they're basically controlling the hardware. They're sending commands to this insert, basically creating the bubble, shearing the bubble, looking at different aspects. There's different experiments we do on here. We're looking at the electric field. We're blowing air across the bubble. We're also heating it, and then watching its behavior, recording it all. And then we have a representative from the science team on hand who either comes in or listens in, looks at the data, and then we provide a summary of what we've seen.
All right, well, let's talk to him about some of the science.
Okay, sounds good.
Thanks, Nancy. I'm here with Dr. Paditha Tin, and he is the project scientist for OASIS. And you're looking for islands, not what we think of as islands, but something like on our phones, on the
cellular
screens. Tell us what those are and their defects.
Right. On the liquid crystal display, like the screens or the cellular phone, once in a while, when during the manufacturing process, there are small little, what you call little imperfections. And then that is what I mean by the islands, okay? Those imperfections are defects, okay? And then as time grows, the defects gets bigger and bigger and larger, and finally the whole screen got destroyed and you're not able to use the screen at all. So essentially we are trying to see why these defects comes together and grow and then destroys the surface of the liquid crystal screen. Okay.
And the space station's an ideal place for that, microgravity.
Right. There's a reason that being is that, see, you're not able to grow or make a very thin film, say like with about 3 or 4 layers, which is about like 10 nanometers thin with 2-3 layers of liquid crystal, and looking at the little islands or defects grows or coarsen. And the best place to study about these, it's in the International Space Station, because it's convective free, and as well as it has no gravitational effect on it. When there's no gravitational effect, the other what you call dominant features like surface tension takes into play, and then that will definitely give us an advantage of looking at how these little defects grows or how they interact. Okay.
And so why do we study this? What will we get out of what you learn from this experiment?
Well, when we learn from this experiment, we have like 4 different materials of liquid crystal with different structures. We're trying to understand how these defects or these structures interacts with each other, how they grow, and then as well as how they can be improved in processing the material so that we will have future liquid crystal, cellular phones or display that has multiple layers. Instead of one pneumatic layer, we'll have multiple layers that we can use the future cellular phone that will come out in the market in a few years that will be holographic, which means that we can talk and then display 3Ds on it. Right.
And it won't crack either.
Yeah, it
right?
will not crack at all. Right. Yeah. Okay.
I need that. All right.
Okay.
Thank you, Dr.
You.
Tin.
Right.
Jennifer Stork is with me now, and she's the operations lead for OASIS. And Jennifer, they're actually running the operations, but this is the first of its kind to actually work with the Russians on an experiment.
Yes, we're one of the first U.S. payloads that utilizes the cosmonauts to do all of our sample installation, all of our consumable swap outs.
That's really an international partnership.
Yes, absolutely, which helps with our the science collaboration as well. We have German PIs and Russian PIs that will use some of our science data. And we run 4 different samples, and our operators here run from about 7 o'clock in the morning, sometimes till 11 o'clock at night. They perform the actual blowing of the bubble and the technical work that needs to be done to get the science.
So how do they do that?
Well, they run several scripts. They watch the bubble. They utilize the PIs on the phone or here to make sure that they're viewing the actual interactions that they're looking for.
I saw a while ago they had to actually suck the bubble back in because it was too thick. So it's tedious work. We don't think about that.
It is, and sometimes you'll get lucky and you'll have just the perfect bubble on the first try, and other times it takes several hours to get the thinnest bubble what they're looking for.
All right. Thanks, Jennifer.
Thank you.